Hi everyone, thanks a lot for joining this webinar. We will talk today about laser communication and atmospheric turbulence. We will be two today to animate this webinar. I'm David Allioux, Product Line Manager for Laser Communication, and I will be with Antonin Billaud. Maybe you can present yourself in a few words.
Hi guys, so I'm the lead engineer on all the turbulence mitigation solution we are developing and selling at Cailabs, either for ground station or for turbulence mitigation, just the optical core. And I'll be the one presenting more the technical side of our solutions.
Thanks. Thanks a lot. And Antonin will show today some experiments live. We'll switch directly to the presentation and we'll start on laser communication. Today, I'm going to talk again about laser communication and atmospheric turbulence and how we can communicate with optics through turbulence. I will develop a little bit the stacks and the challenges of laser communication. I will try to go fast on that because most of you already know probably what are the challenges of laser communication. Then I will talk about our components, our product, how we can demultiplex a turbulent beam and recombine it with a photonic chip to mitigate atmospheric turbulence. Then we will show you our optical turbulence emulator bench. Antonin will do that, and he will also present the results that we recently obtained on this optical bench. Finally, we'll try to keep as much time as possible for question and answer and try to answer as many questions as possible. First, a few words about Cailabs, because I see that there are many people who don't know us very well. So at Cailabs, we are a small deep tech company founded in 2013 around a unique optical technology that we call multiplane light conversion that enable us to manipulate very precisely the shape of the light. Thanks to that, we were able to develop 4 or 5 different product lines, from laser processing with Canuda, where we improve laser machining thanks to beam shaping. We do cutting, welding, additive manufacturing with, again, optical beam shaping. Someone said that they don't have some audio. I don't know if it's the case for all of you. I don't know if it's just Eric. I do have it. I'm sorry, Eric. It might be just you. Sorry. So I'm sorry. I will keep going. So we also have some product where we do optical fiber communication. The principle is to manipulate some different modes inside a multimode fiber to improve local area network. Typically, this is with Arena, or to do very high speed optical communication, let's say invent the optical network of the future with Proteus, where we do different, typically mode multiplexing, spatial mode multiplexing. We also have some custom application where we do everything that is not related to the 4 products that you have on the left. We do, for example, cyber security, aircraft cabling, we do some defense application, and so on. And finally, the product I'm going to talk about today is laser communication with the TILBA product range. I will just say what Olivier Jacques-Samet said on the chat. Again, the webinar is recorded. If you have issues with your audio or anything, don't worry, it will be recorded and you will be able to watch it later. Okay, I go back on the TILBA product. Just in a few words, I'll try to go fast on that. This is more or less what we offer with the TILBA product range, because everybody knows us for the turbulence mitigation product. So I guess it was interesting to show everything that we can do at Cailabs. We, of course, do turbulence mitigation with what we call TILBA-ATMO. It's what I'm going to talk about today. It's really at the core of everything we do in laser communication. But we also can do much more. And typically in some projects, we are doing the subsystem, so integrating the telescope, a tip tilt mirror, even providing the modem and so on. And we are even able to provide the full optical ground station. This is typically what we do with a project with the Ministry of Defense. You see that on the bottom left. We are developing an optical ground station that will be delivered this year before the end of 2022. And we recently obtained a European Commission, EIC, European Innovative Commission, I think, EIC Accelerator project, where the goal is really to industrialize the optical ground station and to be able to provide full optical ground station to our clients. So it was just in a brief word to say that we do, of course, turbulence compensation, and it's really at the core of everything we do in the laser communication, but we can do much more than that. And also, finally, for the presentation of Cailabs, we are a company located in Rennes, in Brittany. It's a very nice country. And what is even nicer is that we will have new buildings end of 2022, end of the summer, more precisely. And as you can see on the bottom right, it will also be the location of our optical ground station, the optical ground station I mentioned in the previous slide. It will be delivered before the end of the year. And if you wish to visit us, you will be able to see it, and we would be very glad to welcome you in Cailabs in Rennes. But now let's talk a little bit about laser communication. This ground station is not ours. It's the one from ESA in Tenerife. But it's typically the place where we want to integrate some TILBA-ATMO and some laser communication. So why do we want to do laser communication? I'm pretty sure you know that very well, and I will try to go fast at that, but just briefly, there are some advantages that are very well known and some that are less known. So at the moment, when you want to do free space communication, the most well-known technology is, of course, radio frequency. The problem with radio frequency is that at the moment, it's becoming saturated, both in terms of throughput, because we are downloading and transferring more and more data every day, but also in terms of number of frequency that you can allocate. Laser communication is a very good alternative for that, or at least a very good complement to radio frequency. It enables ultra-fast communication. Virtually, you can transfer, you almost have an unlimited throughput in theory, at least with optical communication. And it's very common in fiber communication to have more than 100 gigabit of data, even 400 gigabit of data. So it's easy to have very high-speed communication, at least in theory, or at least in fiber. And so it's a medium where you can have very high-speed communication again. It's very convenient also because it's unlicensed. And as I mentioned previously, radio frequency, they start to be limited in terms of number of frequency that you can allocate. You don't have this problem with laser communication because typically the different lasers, the different communication, they don't interfere. So you don't have to have this frequency for this player and this frequency for this other. And finally, it's something that is very interesting for optical communication, especially for sovereign communication or for defense, military, but not only, also when we speak about embassy, when we speak about critical communication. Optical communication is intrinsically secured, or more secured at least, than radio frequency. Its stealth is very hard to detect because you have point-to-point communication, and the point that you have on the ground is relatively small. And it's also very hard to intercept, because if you want to intercept laser communication, you have to be directly on the beam. So it's something that is intrinsically more secure than radio frequency. And even if we imagine the future, of communication and cybersecurity that speak about quantum communication, if we want to have quantum communication in the future, we will need optical communication as a medium, as a backbone. So it's something that is very interesting also for security. But the problem of laser communication, as you all know, is that there is atmospheric turbulence. It's not a problem when you want to do satellite-to-satellite communication, but everywhere close to the ground, everywhere where you have atmosphere, you have atmospheric turbulence. And the problem is that laser communication is more interesting when you have high data rate, typically beyond 10 gigabit per second of data rate. But when you want 10 gigabit per second throughput, you need very small detectors. That's what you see on the right. Typically, it's more or less at scale. When you have 1 gigabit per second detector, you have something that is relatively large. And when you have 10 or 100 gigabit per second detector, you need stuff that are very small, and it's typically something that is compatible with single mode fibers. It's even more the case if you want to use coherent detection, amplifiers, EDFR, everything that is related to standard telecommunication equipment that you have on the ground. So if you want to have high-speed communication, you need single mode fiber compatibility overall. And the problem, as you see on the right again, is that here you see a typical wavefront of a beam after atmospheric turbulence. And as you see, the whole signal is very well detected by a 1 gigabit per second detector. But when you go to 10 gigabit or 100 gigabit per second, you see that most of the signal is out of the detector. What this means is that you need to have atmospheric turbulence compensation, you need to couple all the light that you see here and send it to a single mode fiber. That's roughly the idea. And that's what we do at Cailabs. And for that, we have a product that we call TILBA-ATMO. That's what I'm going to present. And I'm going to go a little back on what we do at Cailabs and typically on our technology, on our core technology that we call multiplane light conversion. As I said previously, what we do is optical beam shaping. We do that very well thanks to our technology, MPLC, that comes from Laboratoire Kastler Brussels. The idea is really to be able to manipulate the shape of the light thanks to a succession of faceplate and free space propagation that acts as a Fourier transform. Roughly, what you need to remember is that with a limited number of planes, you can do an exact conversion between a special base, a special basis to another special basis. So basically, you can modify several beams at the same time, simultaneously, to another range of forms, and really, you can do that simultaneously with the different shapes. So typically, if you look in the middle, we have here several, I think it was 7 Gaussian beam that we transform, thanks again to the succession of faceplate and free space propagation, to a superposition of 7 Hermite Gaussian beams. Or maybe it was Laguerre Gaussian beam. Here, I don't see very well. This is a theory that you see in the middle. On the right, it's more how we implement it, because if you implement it in transmission, you would have a lot of losses. It's also not very convenient. It's bulky. It's very, very big. So what we do is we implement it in reflection. You have on the left a bundle of fibers. So bundle of fibers emit single Gaussian beams. So you have 7 Gaussian beams on the left that we shape thanks to a succession of reflection on faceplate, again, free space propagation that is done through inside a cavity. And with this succession of reflection, we are able to modify the shape of the light. And on the bottom right, what we have is a superposition of Hermite Gaussian modes. So overall, what we do is optical beam shaping, thanks to the tool I presented previously. And we can do very nice shapes like a square that you see on the top left that is interesting, for example, for imaging. On the bottom left is a Hermite Gaussian mode that is interesting for fiber communication or free space communication. In the middle, on the right, those are orbital angular momentum that are, for example, interesting for quantum communication. So basically, we can do every type of shapes, more or less every type of shapes, and single mode transformation, so one beam to one beam, or multi-mode transformation, so several beams to several beams at the same time. And why is it interesting? It's interesting because when we want to mitigate atmospheric turbulence, what we do is spatial decomposition of a wavefront profile and transforming this wavefront profile into something else. Historically, people do that with adaptive optics. What they do is they monitor the wavefront profile with a wavefront sensor, and they modify this wavefront with deformable mirrors. What we do is, in a sense, a little bit similar, but we modify the whole field, so amplitude and phase, where in adaptive optics they play with the phase only. What we do again is the decomposition of the phase on different modes that you see typically on the right here. So the wavefront in the top is really the exact decomposition of the different shapes on the right with, uh, with random amplitude and phase. And thanks to, so what we do is that we have the beam profile that is decomposed on modes. We transform this mode into single mode fibers, and then we recombine these single mode fibers. And maybe the next slide is simpler about that. So let's imagine that we have a Gaussian beam that is sent from a satellite. When it comes to Earth, it's perturbed. This is what you see on the left. We can decompose this perturbed beam on several modes, spatial modes. Thanks to our MPLC, we're able to decompose these spatial modes to demultiplex them into single mode fibers. That's what you see in the middle with Phi1, Phi2, Phi3. Why is there Phi1, Phi2, Phi3? It's because we decompose them inside single mode fibers, but the modes that we have inside these SMFs, they have random fluctuating amplitude and phase. So this means that we have not one single mode fiber, but several single mode fibers with random amplitude and phase. What we know is recombine coherently these different modes thanks to what we call an optical recombiner, and we send that to one unique single mode fiber. And I will come to that, how we do that a little bit later. So how does it look like exactly? So I will develop a little bit each block. The first block is the MPLC. I talked a little bit about that. For the test and the results that we will present later, we had a 10 modes MPLC. This is the version that we have at the moment with approximately 2 dB of loss for the MPLC only, so for the decomposition of the spatial modes. In the next version, we are aiming at 45 modes, and we still aim at approximately 2 dB of insertion loss. What we do with the optical recombiner is combining different single mode fibers into one single mode fiber. How we do that is with a cascaded Mach-Zehnder architecture. We combine the single mode fibers 2 by 2. So typically with the scheme we have, you see in the middle, we have two inputs where each have a single mode fiber. We modify the phase and amplitude thanks to two phase shifters that enable us to have all the power into only one output. So typically, we are able to change the phase of PS1 and PS2 to have all the power in output one, in the output one. So if you cascade that, you are able to have first, imagine you have 8 entry, then you have 4 intermediate entry, then 2 intermediate entry, then 1 intermediate entry. That's really how it works. How we implement that is typically on integrated photonic chip. These are two of the design that we fabricated, one with edge couplers, the others with grating couplers. And what is important here is that currently we have 8 modes that we are able to recombine with our photonic chip. And we have relatively important insertion losses that and so in the end relatively important optical losses at the moment, but we already have strategies to mitigate that, and probably we will come to that in the next slide, and probably in the questions also. And so we now have an 8 mode recombiner. So again, we recombine with the cascaded architecture of Mach-Zehnder. With integrated photonic chip, we have approximately rise and fall time, which is important for the speed of the architecture, that is 7 to 10 microseconds, so much lower than the atmospheric turbulence. And I don't think I will comment on the software too much, on how we implement that, on the algorithm too much. But just in a few words, what we do is a try and go algorithm. So we change a little bit the phase in one direction. We see if the signal improves or degraded, and depending on that, we modify the phase accordingly to always have the best signal at the output. That's roughly how we are able to compensate for atmospheric turbulence. So we have an MPLC, we have an optical recombiner with an integrated photonic chip, and with that, we are able to compensate for atmospheric turbulence. So this is roughly how it looks like. You have on the bottom left an MPLC. You have on the top the photonic recombiner with the integrated photonic chip inside. And on the bottom, it's an electronic control. It's relatively bulky at the moment, but at the same time, it's not really a challenge for us because when you have the photonic chip, you are able to have something much lower if need be. And so that's typically the type of product that we are selling right now. And now I will leave the floor to Antonin, who will talk a little bit more about atmospheric turbulence and show the experimental results that we obtained.
Okay, so let's get started on the part. So I'm going to talk about atmospheric turbulence again, a bit more introduction on that, more work on that. And then I don't think I'll repeat everything that David said because it's a lot of repetition. And then I'll move on to what our turbulence bench is, how it works, what we can do with that, and how we can use that to test our systems and what kind of results we manage to obtain. So first, what is atmospheric turbulence? Why do we have this kind of stuff when you don't have it on other telecom applications? So the idea is that you send usually I'm going to talk about a LEOsat, so low Earth orbit satellite that is sending a beam back on the ground and where you want to collect all the light. So usually what would happen is that you've got your satellite emitting a beam, it's coming down, and then when it's coming down, it's diverging because you've got a huge amount of distance. It's going through different layers of the atmosphere because it's not just vacuum, you've got a lot of air there that has a lot of warm and cold air bubbles. So this causes deformation of your wavefront because you've got a nice wavefront propagating, and then it gets messier and messier as you get down and closer to the ground. So this causes a lot of issues. And what happens is that as this layer is thicker and thicker, or if you've got a low elevation angle, you've got more and more turbulences. And if you look at the beam on a camera, for example, instead of having something really nice, it gets really, really disgusting. So you've got two issues there. Is as the beam propagates quite a lot from the source to the detector, it diverges and gets quite big. So you collect just a tiny part of it because you can't have a telescope that is like hundreds of meters wide to collect all the beam. It gets really, impossible, especially when you want to develop a lot of different stations for quite cheap amount of money. The other issue you've got is the beam is disturbed, so it's a deformed beam that could look like the picture on the right, instead of what you would expect at the focal plane of the telescope, which is what you see at the bottom left. Because what you see at the bottom left is what you would expect without turbulences. That's what people do for use and aim for in astronomy, for example. That's why you go and you put your telescope on top of a mountain in Chile, because you're really high, you don't have a lot of turbulences, and you could do really nice astronomy pictures. But if you were to put your telescope, I don't know, in Paris, you would probably obtain something like that on the right, or even more disgusting. So we've got two issues there. First is you collect just a tiny part of the beam, and second is the beam looks so disgusting that you can't inject it properly into a single mode fiber, which is a big issue because you want to be compatible with all the telecom systems and all the telecom components to do a high debit rate telecom link. So now the question is, how can we do that? How can we make use of all the photons collected? That's what the solution David presented. I'm going to talk about a bit more about how we characterize atmospheric turbulence. So we can use a turbulence bench that allows you to work on different parameters of the atmosphere. Usually when you want to characterize the atmosphere, you can find a lot of papers that talk about that. They use what they call a curve and graphs that are called CN2 that describes exactly how your atmosphere is at a given point in certain conditions. And from that, you can do a lot of simulation and deduce few different factors. For example, what they call Fried parameter, Greenwood frequency, and scintillation index. I'm going to explain this and what are the effects of these ones. I'm just going to talk quickly about that because, if you want to know a lot, don't hesitate to check on the internet. They've got a lot of papers, Wikipedia pages explaining everything on that more in detail. So the first one, the most used one, is fluid parameter called R0, which will determine how turbulent your atmosphere is, which is usually what you do is, if I want to simplify things, when you've got a telescope, what you've got at the focal plane is an airy pattern, just a tiny spot, that as your telescope gets bigger, you've got a smaller and smaller airy pattern, which is why in astronomy you've got huge telescopes. In fact, this is not true when you've got atmospheric turbulences, because you're not limited, the diffraction is not limited by the picture is not limited by diffraction and the diameter of your telescope, but it's limited by the R0, so your fluid parameter. So in fact, if you've got a fluid parameter that is smaller than your telescope, there is no use getting a bigger telescope. You won't obtain a sharper image, for example. So that's the first parameter to take into account. Second parameter is Greenwood frequency. That in fact gives you an idea of how fast your turbulence moves, because you could have different, the same fluid parameter, but sometimes your turbulence could evolve slowly or could evolve quite fast. So this is really also an important parameter. For example, on adaptive optics, you can find solution where you can mitigate turbulences, but if it goes too fast, you can't mitigate it because it's actuators, so you can't follow it when it's up to tens of kilohertz, something like that. Doesn't really happen often, but that's a parameter to take into account. And then you've got a third parameter, which is scintillation index. Scintillation index is, as you just look at a tiny part of the beam, you just collect a tiny part, as I said, because the beam is quite wide when it hits the ground. And you've got some things that the pattern is kind of a speckle. You might be unlucky, and from time to time, you just collect less amount of energy hits your telescope compared to previously. So scintillation index is variation of just the amount of power collected by your pupil of your telescope. So that's also something to take into account. So that's the three different parameters you want to be able to modify and control on your system. So I'm going to explain how this works on the turbulence bench I've got there. So now I'm going to change camera and explain how everything works. Okay, so normally you've got a new camera, both of you. So from the top, I'm here. So what we're using is we're using phase plates, turbulence plates, to emulate the different layers of the atmosphere and then emulate atmospheric turbulences. So it starts here. So you can see me. So I've got a laser that is there that is collimated. So it's collimated, it's giving me my plane wave. So it emulates my satellite. Then it goes onto a first faceplate, a first turbulent plate, which is in fact high atmosphere turbulences. So it's the highest layer of the atmosphere. So usually you've got not a huge amount of turbulences there, but it varies quite fast. And as it's quite high, it's going to propagate a lot before hitting the detector. So what this will cause will not be really a lot of turbulences, but probably a lot of scintillation, because as it propagates, the phase fluctuation will transform into amplitude fluctuation. I'll show you that later on when I run this bench. So I've got my high layer, the highest layer of the atmosphere. I'm propagating. Then I'm hitting a highly turbulent layer that is really close to the ground. So this one has a smaller R0, because as the fluid parameter gets smaller and smaller, that means more and more turbulence. So here I've got my layer just before my detector, for example, before my telescope, which is a high turbulent level. And then just beneath it, I've got my diaphragm that is used, and in fact, that's just a pupil, that's the pupil of my system, so that emulates my telescope aperture. So by taking into account these different faceplates and the diameter of this pupil, I've got my D over R0, which is my main factor to know how much turbulences I will have in my pupil. So that's quite nice, and you can vary all these parameters. Then I've got another setup there when I reimage this pupil onto this particular mirror, which is a fast hearing mirror controlled with piezoelectrics. So this allows me to, in real time, to compensate for tip tilt. Because what you would want to compensate, for example, is as your beam is going to move, you always want to recenter it on the detector. For example, if you want to inject into a single mode fiber, you want to always be able to control it and ensure that the beam, even if it's deformed, it's always centered. So you've got this mirror, which is controlled by a feedback loop with control with this element and a feedback loop with a quadrant photodiode. So I've got my quadrant photodiode detecting a tiny part of the beam, and I've got a feedback loop that controls this mirror to always center the beam on top of at the center of this quadrant photodiode. So that's an alternate path. The main path goes here, where I've got goes here into our detecting system. So I'm going to show another alternate path that I will just use for you later on, which is I've got an alternate branch when I hit just a camera that allows me to look at how deformed this beam is, so how the turbulences fluctuate and things like that. And here I've got my two main path, which has two different telescopes. The first one that injects here into a single mode fiber with the right telescope to match the pupil of my fiber, the aperture of my fiber with the pupil of my system. And then I've got another telescope that injects into my TILBA-ATMO system. So here's the only element of my TILBA-ATMO system I've got just right here is the MPLC David talked about. So what you see is that you've got your beam that is deformed and disturbed and is going to change over time as turbulence is never fixed. It's going into that. It's decomposed into a lot of Gaussian beams, and then it hits all the electronic and the integrated chip, photonic integrated chips that does all the feedback. So what I'm going to do now is show you quickly how the beam behaves depending on which layer the turbulence is moving and things like that. So I'm going to share my screen. It should be working quite well. So normally you should see my screen now. So what you see is my two layers of turbulences, or my two phase plates, they're not moving. Now what I'm going to do is I'm going to move just the top layer, so the one that is not that turbulent, but is at quite a high distance compared to the detector. So what you're going to see now is in fact a beam that moves a lot. You can see the speckle pattern changes a lot, when in fact I'm just applying a small amount of phase propagation. Then I'm going to show you what happens for the lower layer of turbulences, so the one that is just close to the detector, close to the ground. Change the beam quite a lot. I mean, you can see that you don't have this huge scintillation issue where you've got your bright spot that moves quite a lot around. And you can see that both turbulences are quite. I'm going to merge the two of them together exactly at the same speed. You'll see it gets quite messy. Yeah, it's getting really crazy. So you can see that the issue is that because here I'm still going quite slowly, and you can see the issue of how can you follow that? You need a feedback loop that works really well. So either you can be limited on your electronics to follow that really properly, or just even your actuator, because we know that's an issue you can have. System is, I mean, if you can't control everything fast enough, you can't follow all that. So that was a quick demonstration of what we can do. What we can do is we can change a lot of things on this bench depending on where we put our turbulence strings. We can change exactly what kind of scintillation we've got, what kind of, by changing the aperture we use for the diaphragm, we can change also the D over R0. So we can really vary the different configurations we can aim for. I'd say it's a nice turbulence bench to be able to do repetitive and reliable things, because always the issue when you want to test stuff that is made to mitigate turbulence is if you do it outside from one day to another, you never have the same condition and things like that. So you want to be able to do something quite reliable. I'm not going to go in details about all the calculation needed to set up your bench and to know exactly which configuration means what. What you can have a look at is the paper from the owner. I think we put the reference in the slide, which is quite nice. They explain their Piccolo bench, which is a really nice turbulence bench that allows you to do really a lot of different configurations, and explain also the interest of having just more than one faceplate. So depending on what's the advantages of having 3, 4, 5, 6, 7, and like what kind of gain you've got if you've got a lot of face screens compared to just one and things like that. And what you can see in general is like having one isn't really not enough, and usually you want to aim for 2, 3. You can go for higher than that, but then you've got the issue that do you want something really complex to just gain a bit more of accuracy? So that's really, I think that's a trade-off you've got to make on your own depending on what you want to aim for. So now I'm going to go back on the slides to show you exactly what kind of results we obtain with that. So here are some of the results we obtained. So I'm going to present results that were done with our turbulence bench, and some of them that were done in partnership with the owner on their Piccolo bench. So what I'm showing on this slide is what you can see is you've got the SMF, so our single mode fiber how much we can collect with a single mode fiber, how much we can collect with our TILBA-ATMO system, which on the right side is the pink curve, and in red is how much is entering the pupil of our system. So the idea is that you can never do better than the red, because I mean, if the light doesn't hit your telescope, you can't really do anything with that. So the target is to be able to make a system as good as possible that follows the red as much as possible. And as you can see, the system we offer, at least the first result we obtain, we see that this pink curve is following the red one quite well. We see some drops that, I mean, are expected. For example, when you've got a beam that is too deformed, you might not have enough modes in your MPLC to collect all of that, because we do a linear decomposition that is not really infinite. It's not really full. We can have some fast drops that might be explained because we've got maybe we can't follow some events that are too fast, and that's explanation of the right curve. And on the left, what you can see is we are showing exactly what is the average power collected and also the standard deviation. And what we can see is by using our system, we can have a better standard deviation compared to what you would obtain with a single mode fiber. So that's really nice, because usually one of the issues when you want to do a telecom link like that is the issue is fading, which means I've got high enough light, high enough power to just make my telecom link, and then drops really fast. So I lose the link, and by the time I've got enough power to get my link started again, I need to reinitialize everything, and it gets really takes quite long. So you want to avoid these fadings by as much as possible. So that's another way to present the previous results. So what we did is we just show the density probability. So all the results are normalized. And what you want to do is obtain something as sharp as possible and as much on the right as possible. Because so the red curve shows you the density probability for the amount collected by the pupil. Pink one is what you obtain with the TILBA-ATMO, and black one with the SMF. So you can see you've got a huge amount of variation with the single mode fiber, and the more points you've got on the left, the more fading you will obtain. So what we did also is how much we can compensate for high-speed fluctuations. So what we did is we did exactly the same experiment, because we've got a turbulence bench, so we can do exactly the same experiment and just change the speed at which it evolves. So just change the Greenwood frequency without touching any of the other parameters. And what we can have a look at here is the blue curve, which is the theoretical curve, and the orange one. So at low speed, you can see that both of them, they merge quite well together, which seems quite logical, because if it's really slow, you should be able to follow it, whatever the feedback loop you've got. And then as it gets faster and faster, you've got a lot of more and more points where you don't manage to follow it properly. And then when you get really high, it starts to get messy. So when it starts to get messy, that means you hit the limits of your system. So that means you need either to improve your electronics or improve the rise time and fall time of your photonic chip. That's a zoom of it, because I wasn't sure this was really clear on the previous slide, and you can see at really high speed that you've got some sharp drops at some point where we don't manage to follow everything. But when you still look at the trend, it seems much better than the individual modes, because here what you see in dotted line are the individual modes, when you can see that they move really fast, so they seem to fluctuate quite a lot, while we seem to fluctuate not that much by merging all of them together coherently. What we did also is, once we had all our system tested on the turbulence benches, we're like, okay, now let's try it outside with real turbulence, because we know that with a turbulence bench, you can't really emulate perfectly atmospheric turbulence. So you've got some, you never have a perfect situation, especially with the one we've got. We know it's good enough for first test, but it's not a perfect one, because if you want to do a perfect one, you need to tweak a lot of parameters and have the perfect turbulence plates for your needs. So what we did is we did a system where we did a link between two telescopes facing each other with 200-meter link. So you can see on the left one, it's the emitting side. On the right one, it's the receiving side. We did a test, and what we obtained the same kind of things as we expected before. So you've got a lower amount of turbulence compared to what we tested before on the turbulence bench, but we still see the improvement expected. On the right curve, for example, you can see that the SMF seems to drop quite fast from time to time, and by quite a lot, because that's a dB scale, so you can see some drops that are more than 10 dB. And with the blue curve, which is the output of TILBA-ATMO, we don't have these drops, or at least much less often. So this is quite nice, because that shows that we can bring something to the table, which is really interesting when you want to reach high debit rate. And we know that people are evolving and aiming for this kind of high debit rate. And we also tried that with a telecom link. So we did exactly the same, except we changed from a continuous wave laser to a telecom one. And here we did the same thing. We did the kind of test with a 10 gigabit in OOK. And we measured exactly what was the bit rate obtained. So we can see that with an SMF, you were at 6.3, and with this first version of TILBA-ATMO, we're at 8.1 gigabit. So it's quite an improvement. And especially when you look at the, I'd say what we can call the instantaneous bit rates, you can see that the drops are much less sharp with the TILBA than with the SMF, because when you look at the the amount of time when we were under 50%, that means less than 5 gigabit, we're at this for like less than 6% of the time with the TILBA-ATMO compared to 32% of the time with the single mode fiber. And I think I'm going to present my last results here, which are we did a test last October with the DLR, because we know they're working a lot on adaptive optics and for telecom applications. So we used their setup on a 10-kilometer link. So it's a 10-kilometer link, and you can see, so on the left, it's a picture from the receiver side of the emission site. So what we did is we sticked our system in their setup after the fast steering mirror. So we still have this tip tilt compensation to ensure that the beam is always centered. And what we did is we did a quick measurement of how much power we can receive compared to how much power was entering the pupil. So we can receive that we managed to obtain something quite similar. I mean, it's not the best picture, but here you can see the statistics show something quite similar. At least we don't have a huge amount of differences in standard deviation compared to the pupil. So pupil on the left and output of the TILBA-ATMO on the right. What we did also is we did a study of how much a tip tilt improves the results, because what we were expecting to show was that we can maybe get rid of the tip tilt, or at least aim for a tip tilt that is less complicated or needs puts less constraint to the table. Because if you can set your tip tilt, you're always quite happy about that, because that's a moving part that can be quite expensive and quite an issue when you want to go for something really fast. And what you can see in the insert on the bottom left each time is, so blue curve is fluctuation inside the pupil over a few seconds, and purple one is fluctuation of the tip tilt, of the TILBA-ATMO. Sorry. And you can see that you can obtain the same kind of curves. So that shows that we can follow quite well the amount of light coming into the pupil. So these results are quite interesting, even though that was a long link, so a lot of scintillation, but not a lot of turbulences, because the aperture of their system was not that huge. So we demonstrated a lot of things. We also tested our different system in different configuration and different kind of modulation schemes. So we tested up to 50 gigabit per second in NRZ modulation scheme. We tried also DPS key, which shows that it works with 10 gigabit DPS key. So that means that normally we can encode information on phase. So that shows that we should be current detection compatible. We even did more tests in the last few weeks, where we tested 100 gigabit. I think that was DPQPS key. And we also showed on, we also did some demonstration on a 1 kilometer link in-house with a 10 gigabit per second OOK link. And now what we're going to aim for is increasing the number of channels, so increasing the number of modes of our MPLC. That allows us to deal with more turbulences, that allows us to deal with stronger turbulences, and that allows us to also collect more light in general. We're currently working on a new version of the integrated photonic chip for lower losses, and also decrease downtime by improving the electronics. And I think that's all the results I wanted to present you. I mean, if you've got any questions about that, don't hesitate to put them in the chat, and we'll try to answer as many of them as possible. And also, I think we've got, if you've got any more questions, we've got a few papers we can send you, so, like a proceeding for the last conferences we did and things like that.
Thank you very much. I just have one more slide before we finish that shows the let's say past results and roadmap. As Antonin said, in the past, let's say 2 years, and maybe this year too, we try to validate and improve the laser communication product, turbulence mitigation product, but in the future, and even this year already, we are trying to do more to build the first optical ground station, as I said, and then to industrialize this optical ground stations. This is what we will do in the next year, in the next years also. and try to go to embedded application. And this is really the roadmap now of Cailabs to be able to build the all optical chain and all optical ground station. Before I finish, there are two things that I'd like to say. I'd like to thank all the partners that we worked with in the past years. So Onera, CNES, typically for also we worked a lot in their optical bench. That was so we worked a lot on their publication that was in reference of one article of one slide. And also the GLR, who we performed some tests with, and all the partners we worked with in the last years. And maybe before we go to the question, if you have ideas of next webinar that you would like to see in the future, don't hesitate to write it in the comment or in the Q&A or in the question, and we will try to do it in the next month. So thank you very much, and we'll take some questions. And I guess Olivier, who is in the backstage, will will show the questions. What is the bandwidth of operation of TILBA? So there are two questions. There are two answers to that, because I also saw some questions on the wavelengths in general. First, the wavelength is 1550 nanometer. We choose this wavelength because it's what is becoming a standard when we look at the SDA recommendation or CCSDS. Everybody now is going to 1550 nanometer, and so we believe so it's okay. So we believe it's a wavelength of let's say the coming standards, and the bandwidth. I would say the C-band, and I don't know if you want to comment on that.
So it depends what you talk about, because as you saw on the slides David showed, we've got multiple elements. So usually if you talk about just the MPLC, for example, that we can sell on Proteus and things like that, we can aim for something that works quite well on at a specific wavelength with plus to minus like 5 to 10% wavelengths. The issue is that we use an integrated photonic chip, and it's not really easy to optimize the waveguides in it to be really quite broad. So I'd say you can work on the C-band, but you will have some fluctuation. So it will work quite well. It's probably just the losses of the system which will vary depending on the wavelengths.
Thank you. Does 45 mode mean combining 45 single mode fibers at the end? The answer is yes. Okay, so so yes, maybe to go a little bit before, yes, it's 45 modes that we recombine in the end, and we are doing a photonic chip for that also. And this polarization important, yes, also because the photonic integrated chip is today admitting only one polarization, and also we are working on that to have components that will be, I wouldn't say polarization independent, but that we admit different polarizations. Today, so it depends a little bit, and maybe I will let Antonin comment on the photonic chip. Today, what we can do with the MPLC is roughly, we have, I wouldn't say off the shelf, but almost on the shelf 45 modes components. So we can manufacture and sell components with 45 modes that are demultiplexed. The photonic chip currently has only 8 modes, and we are working on the 45 modes. And with that might be delivered, I don't know, you on the roadmap of the 45 modes?
Yeah, end of 2022.
Okay.
And if we talk just about the beam shaping unit, so for example, the component you see there, so far we've got a 45 mode one that is kind of a standard. And if you wanted to go for higher than that, I'd say we don't really have a limitation. It's really depending on your needs, because as you increase the number of modes, it gets more and more complex. So probably you'll have more and more losses, and also the standard components are not really off the shelf. For example, if you were to aim, I don't know, for like, I want to do 73 modes, I mean, usually people are asking for fibers at the output. So that means a fiber array, and a fiber array that has 73 single mode fibers is not really standard, it's not really reliable, and things like that. So theoretically, we don't really have any limit. Usually the constraints are more like on the kind of, I'd say, price. Also, Yeah, I mean, that's always a factor, because as it's going to be custom components, the price is going to be quite dependent for the quite important for the client, and also performances you're aiming for.
How mature is mode decomposition mode to compare to adaptive optics? That's a complicated question. Maybe to answer that, there will be two factors. First, when we talk about the MPLC, it's fully mature. We sell many of them. We even have components that you can put inside aircraft for aircraft cabling. So the MPLC is very mature. Then there is the photonic integrated chip and the recombining. That is that we are more doing some development on it. Today, what we have is a lab version. We're working on industrialization of this product. So that's for what we do. Then I'm not very good on adaptive optics, because that's not what we do at Cailabs. I'd say today it's something that you need to have somebody close to it working on it. So I don't know exactly how mature it is compared to adaptive optics. I would say probably more or less similar. It's probably easier to use, and at the same time, there are more demonstrations probably on adaptive optics. So
yeah, adaptive optics have got a lot of background, because it's been existing for like tens of years. I mean, we know that mode decomposition, the way we do it with a multiplane light converter, it's been just like 10 years. But then the advantage we've got, if we just talk about this brick, this part, is that our one is passive. So that means that it's quite robust and it's quite mature compared to adaptive optics, which gets usually complicated. But then it's always the same issue, is that when people aim for mode decomposition or adaptive optics, usually they've got a need, and a particular need which is more R&D than just something quite standard. So you try to always push the limit. So it's never mature enough, I'd say.
And maybe to finish on that, our goal, of course, at Cailabs is to have something that is industrialized, that you can put easily inside an optical ground station or inside a boat or inside anything. And it's really the goal that we have now. Which is turbulence in terms of that you can simulate.
So Allioux we can simulate. We can simulate on that. So depend on the who you buy your faceplate for, what you specify and things like that. So the Allioux we can aim for here is roughly from 2 millimeters to something around like 300 microns, something like that. But then you usually don't really just care about the Allioux. You also care about the aperture you can put behind it, and with the diameter of your system. So if you take into account the D over R0, we can go from like 1 to 15, something like that. So why are we using free faceplates? I mean, usually when you look at all the papers and all the explanation and mathematical explanation behind it, it's free faceplate is usually the nicest way to have something quite similar to what you would obtain if you were to do the perfect CM2 profile, and also the easiest one to achieve something quite close to it.
What is the maximum time that you can represent with? I guess that's for you too. So maybe for people who don't read it, which is the maximum time that you can represent with this faceplate? I guess it's a Greenwood frequency probably that you are talking about.
I'm not sure. I'm not sure I'm following this question.
Maybe, yeah. I guess it's the speed probably. We can answer on the speed. Right now, I don't know what is the Greenwood frequency.
So we can reach Greenwood frequency that are like up to 300 hertz. I think the maximum we can reach with the bench we've got is 400 and 400 hertz. And if you're talking about the amount of time, like the longest sample we can take, that depends on the speed of your faceplate. So if you want, you can maybe if we didn't answer the question, don't hesitate to ask it again in more details.
Or by email. I don't know how many.
What was that for you?
You are considering only downlink here. Can TILBA be used for pre-computation or uplink signal? That's a very good question. In fact, what we are targeting right now is more Earth observation, because what we see at the moment is that it's a sector that has that will be the mature the earlier. So we already see some applications, some needs for downlink of images or stuff like that. Telecommunication, at the same time, it's probably the best potential, and at the same time, it's probably coming a little bit later. So that's for the first part of the question. And for precompensation and uplink, I will answer yes, we can do precompensation. We never did that. It's I would say in principle we can do precompensation. I would be very happy to work on that. So if you are interested in, I don't know, partnership or anything, we would be very happy to work on that. And finally, maybe something we didn't talk about at all today is coherent beam combining. This is something that we can do with this type of components. And it's something that we are working on typically on a project that is called COOP with the French ecosystem of laser communication. So yes and yes. Agnostic, or is still agnostic, or can it be used to transmit polarization multiplex signal and polarization and codec signal?
So the answer is yes, because we did some demonstration with DPSK and we're doing some demonstration on DPQPSK. Gets more complicated, but we can deal with that.
And in terms of other type of modulation, it's also compatible with other type of modulation.
Yes, we wanted to make it smaller. So far, we're working on improving the performances before reducing the volume. But yeah, we can make it quite smaller.
Yeah, it depends on your need. So just tell us. So yes, the telescope we're using have a central obscuration. So yes, they block part of the beam. So they block like 20% of the light, which is an issue. But we know that all of the large telescope will be like that. So we've got to learn to deal with that. And I guess this will be the last question. Which distance between telescopes did you estimate Greenwood frequency in your conditions? I guess that's also for you.
So that's a question for me. So distance between the telescope was 200 meters. I don't have the exact number, and Greenwood frequency we calculated it approximately from pictures taken with the camera at the receiver side. It's not really easy to have an accurate number, but value was like between 50 and 100 hertz, depending on the measures we took.
So thank you very much. I don't think we answered all of the questions, but don't worry, if you have some other question, please contact us, please send us some email. We will be very happy to have a phone call with you or to answer it by email. I'd like to thank, of course, Antonin and everybody who was in the backstage and who helped us for the organization. And of course, I want to thank all of you who participated to this webinar. And again, don't hesitate to send us some email if you have some questions, if you want to discuss anything related to TILBA-ATMO or optical ground station in general. So thanks again, and see you soon.
Goodbye. Thanks, guys. Bye.